Hello guys, this is MinhyeokChoi3rdL33 third grade lesson 33. Let's get started. Half and half. A figure has symmetry if it can be folded along a line so that the two parts match exactly. The line is called a line of symmetry. Some figures have one or more lines of symmetry. Some figures have no lines of symmetry. Tell if the blue line is a line of symmetry, right? Yes or no? Okay, so line of symmetry just means that if the figure is folded on the line, would it be the exact same? So for number one, the blue line is right here. Just like that, it is right there. So when we fold it, this side would come here and land right on top of this side. So is the other two sides. So yes, the blue line is a line of symmetry. Number two, let's look at it. If we fold it along this blue line right here, this is gonna come here, and this bottom piece would come like that. So no, that is not a line of symmetry. Number three, let's look at this. The shape is like this. On the other side, it's the exact same. If you flip it, it would remain the same. So yes, that is a line of symmetry. Okay, so let's look at this one. It's a perfect circle, so obviously we know the shape. If you fold it, it's gonna be the same. Let's look at the smiley face. If this half is folded over, it would come like this, which is what is shown. If this circle is flipped over that blue line, it would come here. So yes, it is a line of symmetry. Number five, we could see that this line is slightly lower than this line. So when we do flip it, this line right here is gonna be a little bit higher than the one on the left. So this one would be no. Number six, this diagonal line would come right here. So would this line here and the curve. So yes, it is a line of symmetry. Slides, flips, and turns. A plane figure can be moved in different ways. Slide the block, flip the block, turn the block 180 degrees. Tell what kind of motion was used to move each plane figure. Right, slide, flip, or turn. Okay, so number one, let's look at it. So slide, let's just call this figure number one and this figure number two. So if figure number one was to slide, it would move in either this direction, left or right, or this direction, left or right. So we know that it is not slide. And flip, it would flip here and become like this or like that. And clearly 2 is not one of the options, so it is not flip. When we turn it 90 degrees, it would come right here. When we turn it once again, it would come just in the place where 2 belongs. So this one would be turn. Number 2, we have this line in the middle, and this triangle would have to be flipped over, meaning this point right here is going to come right here and become that exact same triangle. This one would be flip. Number 3, we could see that there is no rotations or no flips, but it just moves a little bit to the right. So that would make it slide. Number 4, same thing as number 3. Only movement we could see is going to the right, so this would be slide. Number 5, we know that it's not slide. Number 5, we know that it's not a slide because it would either be here or here. However, it is not there. And this would also not be flip, because if you flip over this line, it would become like that. And if you flip over this line, it would become that. So this would be turn. Number 6, this could be a slide. However, if we bring this number 1 figure over to number 2, it would end up looking like that. And that does not match up. So this would be flip over this line right here. Tessellations. When plane figures combine to cover a surface without overlapping or leaving any space between them, those figures tessellate. The repeating patterns formed by the figure is called a tessellation. Tell if a figure will tessellate, right? Yes or no. Okay, so number 1, we have an oval right here. If an oval is put right next to it, there's a gap right here. Also right here, so no, it will not tessellate. Number 2, if this is a rectangle, if rectangles are stacked up each next to each other, there will be no gaps between them, which makes it possible for it to tessellate. Number 3 is this is a square, so if this same shape comes around the square, it would tessellate. Number 4, this is a pentagon, and it would come like that. However, when we do cover here, it would leave a gap just about right here. It would leave a gap. It would leave a gap right here and the gap right here. And there is obviously a gap right between the pentagons, so this would be no. Number 5, this is a triangle, and you could keep going with no spaces with the triangles. So yes, this one, it's a hexagon. So hexagons, if you put it next to each other, it would tessellate, and another hexagon could fit in these places. So yes. Number 7, it's a circle, so obviously it does not tessellate. No circles could tessellate. Number 8, it's a square. This one is obvious. There is no space, so yes. Word problems. Pillar says that a pentagon is a tessellate. Do you agree or disagree? Okay, just like the question we had above, this is a pentagon. When we put another pentagon, just like that, we do not have a pentagon that could fit in this gap right here, and it would always leave a gap between the pentagons, so disagree. Why can an oval not become a tessellate? Just like number 1 that we did up there, if an oval is placed next to each other, there will always be gaps somewhere between the ovals. Nathan has 19 large shells and 17 small shells. How many groups of 4 shells can he make? So that'd be 19 plus 17, which would give us 36. And 36 divided into 4 groups, we would get 9. Rex says that a square is not a tessellate. Explain his error. Okay, so this is a square. Sorry, I'll draw. This would be a square and a square placed next to it. in the square, square, square. He made a mistake because there would be 0 space left between the squares, which makes it a tessellate. That's it for today. Thanks for watching.